Welcome, everybody. It's my pleasure to introduce Connor McCranie and Markus Pflaum from CU Boulder, and today they'll be telling us about catastrophe theory.
All right, thanks, Henry. So catastrophe theory, what is that? So for some motivation, in calculus, in a physics class, all over mathematics, really, we like to deal with continuous functions. So we want to assume that a small change in input will lead to a small change in output. So some examples where this works really well: speed of a car, motion of a planet, amplitude of a wave. Continuous functions are a good model for these kinds of things. But in the real world, there's other phenomena that don't act like this. Sometimes when you change your parameters, even ever so slightly, it leads to a dramatic change in behavior. So for some examples, water freezes. If you continuously change the temperature of the water, it'll have some behavior of being liquid, but then there becomes a critical temperature where all of a sudden the water, is going to freeze, and that's going to be the new equilibrium. Similarly, earthquakes as a continuous function of time, stock market crashes. Our camel is fine with straws on its back, and suddenly when we add one more straw, we get a very different behavior. So catastrophe theory tries to understand these situations, where they're coming from, and to try to classify them and see if we can use that in some applications. All right, so in this talk, we're going to have a function of some amount of variables. The first n of our variables are going to be intrinsic to the state, so the x1 through xn. That'll be our variables that determine the state of the system internally, and then the u1 through ur will be some sort of external parameter. So for example, in the water, with the water freezing, the external parameter is the temperature changing, and so the u's are going to be external perturbations. And so in this context, for thinking of f as being a potential function, then a critical point of f corresponds to an equilibrium of the system. Local minima of f are stable equilibriums, but other critical points are unstable. So some terminology: a critical point of function f is non-degenerate if the Hessian matrix is invertible. So the Hessian matrix, we just do the second order partials of every possible choice and put them in a matrix. And so if the determinant of that matrix is 0, then it's degenerate. But if that matrix is invertible, then it's non-degenerate. So sort of the opposite of catastrophe theory is Morse theory. So Morse function is one with no degenerate critical points. So all of our critical points have invertible Hessian. And for the one-dimensional case, this just means that our first derivative is 0, but our second derivative is not 0. So for the rest of the talk, I'm just going to assume that P is the origin, because we could always translate by P and have an analogous statement. It's just easier if I always assume that P is 0. And so the behavior around non-degenerate critical points is actually pretty well understood. So there's the following theorem called the Morse lemma. Suppose we've got a smooth function of invariables, and f of 0 is 0. Then non-degenerate critical point of f is of the form, 0 is a non-degenerate critical point of f if and only if there exists some neighborhood of the origin and some local diffeomorphism, which fixes the origin. And when I compose with f, I get into this form. So let's maybe kind of break down a little bit what this is saying. So local diffeomorphism, you can think of as just a change of coordinates. So this is saying that up to some sort of change of coordinates, which doesn't change where my point is. So here my point is 0. After the change of coordinates, around my non-degenerate critical point, I can write it in this form, where some of them are minuses and some of them are pluses. So let me take just a quick example in 2 dimensions. We have, it could either look like x squared plus y squared, could look like negative x squared minus y squared, or x squared minus y squared. Those are the only options for a non-degenerate critical point. So x squared plus y squared, it just means that that critical point, up to change of coordinates, locally it looks like this, where it's just a minimum. Obviously for negative x squared minus y squared, it'll just be this upside down, so a maximum. But if I do x squared minus y squared, then we get, calm down. We get just sort of this typical saddle point. So in higher dimensions, the same kind of thing happens. The index I, the number of negative signs, is the number of directions around my point where the function is decreasing, whereas the number of plus x squareds are the number of directions it's increasing. So maybe you could kind of imagine how this would work in 4 dimensions or higher. Same principle, it's just the number of directions it's decreasing or increasing. Okay, so if we have non-degenerate critical points, we can always get them in this nice form. Like I said, the index I represents the number of directions that it's decreasing. So remarkably, the set of all Morse functions is dense in the subset of all smooth functions. So what that means is that if I'm given any smooth function, then if I slightly deform it by the slightest amount, I will be able to find a Morse function that's extremely close to it. So even if I do have degenerate critical points, if I make a slight perturbation, then it will become non-degenerate. But catastrophes come from functions which aren't Morse. So we're going to look at how degenerate critical points can actually lead to catastrophic behavior. So for example, let's just take the one-dimensional case and look at the function x goes to xn, x to the n. So if n is bigger than or equal to 3, then you just take some derivatives using the power rule. You can see that the origin is a degenerate critical point. So let's take a look at kind of what that means. So here I've got y equals x squared, which we saw was Morse. And so if I change sort of an external parameter here, we can see that as I change the parameter smoothly, the local minimum also changes smoothly. And remember, we're interpreting it as a potential function. So this would be the equilibrium of the system. As we continuously change the parameter, the equilibrium also changes accordingly. In contrast, if we look at x cubed here, then as I change this parameter, so if my function's in this state, this is our equilibrium here, I can smoothly change the external parameter, and my equilibrium smoothly changes as well until I get to this point right here where it's no longer a stable equilibrium. And then if I change it any further, then there's no minima. And so my system all of a sudden completely changes behavior, and the potential goes all the way to negative infinity. So this is, I mean, this might be something like falling into a black hole. More realistically, though, if we look at x to the 4th, then we can have, so let me set up these with 0. We actually have multiple sort of degrees of freedom of how the external parameters can affect the behavior of this critical point. So here, if I change a, we've got a local minimum, so we'd have a stable equilibrium. If a becomes negative, there's still equilibrium at the origin, but now it's unstable, and we've got 2 new stable equilibria as well. If I change b here, then it's going to also change how these equilibria are related. So for this example, I actually like to think of a seesaw. So imagine that I'm on a seesaw, and there's no weight on the other side. So in this bottom here, this is my equilibrium. I'm just sitting there, and now on the other side of the seesaw, I'm going to slowly add weight. So as I add weight, I'm still here in this well. The equilibrium is just going to stay there. I'm going to stay on the ground until we keep adding weight, until at some point there's exactly my amount of weight on the other side, and this critical point becomes unstable. So I will still be at the bottom of the seesaw, but I will feel weightless. And then if I add even 1 gram more, now the seesaw completely goes to the other side, and the behavior changes suddenly. So this is kind of how, if we interpret our function as a potential function, degenerate critical points of that function lead to catastrophes under perturbations by external parameters. Okay, so when we're trying to understand critical points, we kind of only care about immediately around that point, in some sort of small neighborhood around there. And so this leads naturally to the definition, where we consider 2 smooth functions to be the same if there's some neighborhood around that point that the functions agree on. So if right around my critical point my functions agree in some sort of small area, then I'm going to consider those the same even if they differ a little bit further away. And so the equivalence class under this relation is called the germ of f at 0. So it depends, of course, on the point that you choose. And then also, if my critical point is just sort of an artifact of my coordinates, for example, if you have something in rectangular coordinates and you go to polar coordinates, sharp turns might turn into curves, and I don't want to consider any weird critical points that I get by doing something like that as different. And so we're going to consider 2 germs to be the same if I can compose with a local diffeomorphism to get from one to the other. So if I can change coordinates to get from one germ to another, then I'm just going to say that those are equivalent. Okay, so now we want to talk about the notion of how degenerate a critical point can be. As we saw in the demo, there's sort of a way that we can talk about degrees of freedom in different ways that the degeneracy of the critical point can affect the behavior of the system. So for example, in the demo, I looked at x cubed and x to the 4th. The origin is a degenerate critical point of both, but for x to the 4th, if I took another derivative, it would also still be 0. Whereas for x cubed, if I took another derivative, then I get something which isn't 0. And so we want to think of this as x to the 4th as somehow being more degenerate than x cubed. And so for this one-dimensional case, the number of additional derivatives past 2 that we have to go until we get to something non-zero is called the codimension of f. And so for the one dimension, it's just k minus 2, just from the power rule. So with the reason why we subtract 2 is because 0, with that definition, 0 is a non-degenerate critical point if and only if the codimension of f is 0. So if we take the first derivative and then the second derivative is non-zero, then we'd have to take 0 many more derivatives past that to get to something non-zero.
Sorry, can I ask a really clarifying question?
Yeah, go ahead.
Are you working only in a space where your functions are only up to order 2 in the coordinates? Like, I mean.
No. So that was for Morse functions. It could be shown that there's a change of coordinates where you can reduce it down to order 2, but in general we could have arbitrary terms. Yeah.
Okay.
Any other questions? Okay, cool. So for the mathematicians who are wondering why this is called codimension, it's because of the general. So the actual definition involves looking at the set of all germs around the origin. In fact, this set has a lot of algebraic structure. It's an associative unital algebra over R with operations defined in the obvious way. sum of the germs is germ of the sums, and so on. It has a lot of nice properties. It's a local ring. It has a unique maximal ideal of the set of functions which vanish at the origin. And so for a germ, we can define the Jacobi ideal as the ideal generated by the partials in this ring. And so the actual definition of codimension is just the dimension of that maximal ideal mod the Jacobi ideal. But if that didn't make any sense to you, that's okay. Just think of the codimension as measuring sort of how degenerate a critical point is, the degree of it, the degeneracy. And so there's this famous theorem due to Thom. So classification of critical points with codimension less than or equal to 4. If we have a smooth function which has which f of 0 is 0 and the first derivative of f is 0 as well, then we can so they've classified all functions with codimension between 1 and 4. And what it turns out to be is there's these 7 called the elemental catastrophes, and we can break our function into one of these catastrophes plus some non-degenerate quadratic form in the remaining variables. So if we recall to the beginning, there was the theorem about non-degenerate critical points being able to be written as a non-degenerate quadratic form. So what this is really saying is, if I have a degenerate critical point, then this function can kind of be broken up into the degenerate part and the non-degenerate part. And so if the codimension is less than or equal to 4, then the degenerate part is one of these 7 functions, and everything else must be non-degenerate. So are there any questions about this statement? It's a little wordy, but.
Yeah, question. So this is for functions defined on the plane. And
so this is for functions from Rn to R.
And so, so if I'm looking at R3, it turns out that the z coordinate doesn't need to be used to describe any of these.
Well, so that's where the Q comes in. So if I have some sort of critical point, then it's gonna, let's say it's gonna be x cubed minus xy squared for the p part. So it says that the p part has to be one of these 7, and then the other, it would be plus z squared or minus z squared. So there'd be a non-degenerate quadratic form in the remaining variables.
Right,
So
but sort of like all of these degenerate behaviors can be described just by like 2 coordinate, which is sort of surprising to me at first.
Well, at least for codimension less than or equal to 4. Yeah. This has been generalized, excuse me, to higher codimensions to 5 and 6, and there you do get things that have 3 variables. But the point is, if I'm working in R17 and I know that the codimension is less than or equal to 4, then the degenerate part really is only coming from 2 of the variables.
Cool, thank you.
Yeah, good question. Okay. All right, so as an example, if we have some sort of function, then we can compute its total derivative and its Hessian matrix. In this case, they're both degenerate at the origin. You can compute the codimension, and it turns out that it's 2 in this case. So by the classification theorem, then we must have that it has to be one of these. And so you can actually check and find a local diffeomorphism, which you can compose my original function to here. So it's kind of like, you know, it's nice to have these sort of canonical representatives. If I have a function and I want to figure out how it behaves around this critical point, then I can look at my finite list and figure out change of coordinates to get to one of those. Okay, so now
question, Connor.
Yeah.
And is it easy to find that diffeomorphism in every case?
No. In fact, well, at least I had some difficulty doing this by hand. it took me probably a couple hours.
No,
to
but
figure
for
it
a
out.
general function, let's say we want to model, our energy landscape of, n-dimensional, 3n dimensional reaction. Is there an algorithmic approach to finding this diffeomorphism?
Yeah, so actually this ring of germs that I talked about earlier, it looks, you can think of it as just being power series up to but you have to remember that there are flat functions. So there are functions which have 0 Taylor series in some neighborhood of a point, but aren't themselves the 0 function. Those are called flat. And so up to addition of one of these flat functions, everything, all of my smooth functions look like just Taylor series. And so you can use known computer algorithms that use Grosvenor bases and stuff like that to work with power series, and that's a lot easier to do with a computer. So I don't know of the specific algorithm for this type of thing, but I know that there is a way to think of it as power series, and computers are pretty good with that.
Okay, thanks.
Yeah. Okay, so we want to talk about unfoldings. So this is going to be a higher dimensional function. So it's starting with more variables, but if I just put in 0 for all those extra variables, then I get back to my original function. So I'm sort of increasing the dimension and adding extra variables that are going to serve as my external parameters. And I want to look at how this changes as my extra parameters change. Okay, so again, we're thinking of the first variables as the internal variables, and these new variables that I'm adding as external influences. So again, if it's going to be an unfolding, if when all of these u's are 0, in other words, I'm not changing the system at all, then it just reduces down to my original function. Okay, so for each set of, for any sort of external conditions, we get a function, f sub u, which just evaluates my system at those parameters. And so, yeah, so f sub u gives the potential of the system under perturbation by u. And now we've got some terminology. So the catastrophe surface is all the points in R in plus R, where my derivative is 0. So these are going to be kind of the points that I care about. The catastrophe set is a subset of that. I just look at the subset where the Hessian is not invertible. So of all my critical points, the catastrophe set is all the ones that are degenerate. And then the bifurcation set is the projection onto the parameter space. So which parameters lead to degenerate critical points? So let's look at an example here. Oh no, hold on, sorry. All right, cool. Can everyone see that again now? All right, so in this, so let's just look at the top left here. So here I've got this shape, and it's going to be rolling on the ground. This red point indicates where it will come to equilibrium on the ground. And this green point is the center of mass. So that's the external parameter in this situation. I'm going to be able to change the center of mass. And as a result, I'm going to see where this shape would come to rest on the ground. And this yellow line in the left-hand box, this is the potential of the system. So as you can see, when I move the center of gravity, it affects the potential function. And my red dot here is always landing where there's a local minimum of that potential function. Okay. So this dotted line here, this represents this is the bifurcation set. If I move my center of mass into here, then if you look at the potential function, it suddenly now has 2 critical points, 2 local minima. So it would stay at rest here, But if I tilted it over all the way to the other side, it would also be able to come to rest over there. And there's actually some catastrophes happening here where if I move the center of mass past this critical point, then suddenly it would swing over to one side. So again, you see as I continuously change this center of mass parameter, my shape is continuously changing where it's coming to rest, but then at some point it would suddenly swing over to the other side. Okay, so now let's take a look at this.
Can I ask a quick question based upon this? So you
Yeah.
mentioned the catastrophe surface in the previous slide. So the catastrophe surface for this system would look like what?
So yeah, so that's what I'm about to explain. So over here on the right, this orange mesh is the catastrophe surface. So it's just plotted in part of it is plotted. This blue line here, this is the catastrophe set. So the orange mesh is all the points in my configuration space where the derivative is 0. This blue line is a subset of it. Again, I've only generated part of the orange mesh to try and keep things to a minimum here. So the blue part is the part where the Hessian is degenerate. Okay, and then if you look here, we can look from the side, the projection of the catastrophe set here ends up being the bifurcation set. So I'm projecting down to just my parameters. And sort of, I guess the takeaway here is that in my higher dimensional space, this curve is actually smooth. I don't have any degeneracies, I don't have any singularities. But in my original diagram, I had this, because I was looking at it from a projection, it had this singularity. And sort of that's kind of the takeaway with these unfoldings. So what it's saying is, yeah.
Can I pull you down and ask some questions about that demo?
Yeah.
So you had like the 2D picture and you had the 3D picture. So the 2D picture, are we living on the real line? Sort of like we have the real line and we have some ground height, and then you have some ball that's like.
So our function here is the center of mass of the, so we're living in R squared. It's taking a XY coordinate of the center of mass and then going to the position of the center of mass, so to R.
So even in the upper left plot, we're taking the bird's eye view over the flat Earth, which has an X coordinate and a Y coordinate. Is that right?
Yeah. So we're taking, so over here, if we take a cross section, then that's a particular set of external parameters. So that's a particular center of mass.
Right. So the third coordinate that you're plotting is this external parameter, the center of mass. But like, what is this a center of mass of, or like, or?
It's of this shape. This
I see.
This paraboloid looking thing. Yeah.
So the paraboloid looking thing is just some shape, and then as you change the center of mass, it rotates, or it.
So here the ground is actually changing because Sam is the one who actually made this demo. He said that it was easier to get the ground to move as opposed to making this thing to move.
I see. Okay, so the ground is
really the ground is staying still.
The ground is the dotted blue line.
Yeah.
I see. So as you change the center of mass, you see the shape rotating.
Right. It's not. You kind of have to use your imagination a little bit because the ground should be the one that's staying still and it's rotating. Yeah.
And then the red point is where the shape touches the ground. What's the orange curve?
So that's the potential. So using the sort of equations of Newtonian motion, I guess, it'll compute what sort of the potential is. So if I was if the center of mass is here, for example, and then I, put the shape in a state where it's rotated slightly, then the potential is going to be higher, and so it'll come back and down and rest where the center of mass leads it to rest.
And then what's the catastrophe that happens again for this shape?
So here, if I'm inside of this bifurcation set, so I get these two minima. So this would be a sort of a change in behavior where now the shape is able to rest on both sides.
I see.
And then if I were to change it in this way, then it would suddenly roll over to the other side.
I see. So, right. So if the shape is, if all the mass is like near the flat part of the shape, then I could rest on this end or on that end.
Right. Exactly.
Mass, one of those is going to become no longer balanced and it's going to flop to the other side.
Yeah, exactly. When this center of mass is really close to the flat part here and in the like near the center, it's kind of unstable. If I change to be on one side, then it'll rest on that side. But only a slight movement of it to the other side leads it to also want to rest on the opposite side. And so
and
if somehow
I'm going to get the vocabulary wrong, but you'll correct me. So in 3D, the blue curve is the bifurcation set.
Yeah.
And then when you project it down to 2D, it now has this kink in it, and then it's called bifurcation.
Bifurcation set. So for the first one, in 3D, it's the catastrophe set.
Catastrophe set. I see.
Sorry. Yeah.
Yeah. Okay. Cool. Wow.
Yeah, there's a lot going on in this.
Yeah. Sam did a very nice job making these, and yeah, thanks for your nice job sharing them. Cool.
Any other questions? Okay, so these unfoldings, it's like I've got this degenerate critical point, and I want to lift it to a higher dimension so that I can have more dimensions to kind of unfold this nastiness at that point, just like we saw in the demo. And so there's a notion of a universal unfolding. So it's a universal. So an unfolding is called universal if every other unfolding of the same function factors through it. So essentially this diagram is going to commute. So if I lift my function to add r external parameters, and then I lift it to have an additional parameters, then it's called universal if the unfolding I get from the higher amount of parameters could have actually gone down to the lower parameters first. And essentially I'm just adding pointless extra parameters. And so these are kind of like primes. It's almost like the prime unfolding. It's any unfolding you have is going to have some universal unfolding at the bottom. So there's obviously a lot of mathematical questions about, do these things exist? What are my conditions on the commuting map here? Do they always exist? It turns out that they do if the function has finite codimension. And so that means that every one of our catastrophes from the classification theorem earlier has its own corresponding unfolding. So each of these catastrophes we can lift to a higher dimensional space into an unfolding where it sort of smooths, is enough space to smooth everything out. So let's go back to this 3D graph here. Okay, so here's the unfolding of the x cubed. So if you look here, so it's all one piece. We're going from, we're adding an additional parameter into our input space. And so we get a 3D surface instead of a 2D graph. And if you look at any of these cross sections, they look like cubics. As I was varying the A, the sort of intensity of this cubic was changing. And here we're just stacking them all next to each other in an ambient space of higher dimension. And as you can see here, this point, with the critical point at the origin, is actually no longer degenerate. perhaps you could try to imagine a change of coordinates in which this looks like a saddle. So we've got this part going down over there, this part going down here, and then we've got going up in the other direction. So in a higher dimensional space, we were actually able to make this point non-degenerate. Okay, so this is the fold. This is the unfolding of x cubed. The unfolding of x to the fourth is called the cusp. And unfortunately, you're going to have a pretty good imagination here because there's too many dimensions. So it would actually be a 3 manifold in 4 space. As I vary u here, you would have to kind of extend it into 4D and stack up all those slices next to each other. But the theory of it all proves that it is actually an unfolding, even if you can't really imagine it. So for all of these catastrophes, we can actually lift them into higher dimensional space and get sort of an entire object that encodes all of the information about my catastrophe. Here, there's an interesting paper where they used curved mirrors to represent these things in higher dimensions. So this one was all of them have these names which correspond to them somehow to the shape of them. So here's the swallowtail unfolding. They use curved mirrors to attain this, and they do different cross sections here. And so, I mean, I think it's pretty cool. They've got the numeric, what it should be according to the function, and then this is the experiment. So as you can see, these things really do happen. And so here's the bifurcation set of the swallowtail unfolding, different cross sections. And again, the experiment very accurately matches the predicted numerical result. Here we go, when you go to the butterfly unfolding, which is of x to the 6th, it's even higher dimensional, and so there's a lot more cross sections. But even still, the experiment matches the numeric results pretty accurately. And so now Markus is going to tell a little bit about how catastrophe theory is going to help us for the Delta project and where it comes in for chemistry. So Markus.
Yeah. Thank you, Connor. So Connor, at the beginning of the webinar, mentioned a couple of applications of catastrophe theory, like describing earthquakes or freezing of water. And in the last part of this webinar, I would like to explain an application of catastrophe theory in chemistry. This goes back actually according to work by Bader from the late 70s and early 80s, and later to work by Sylvie and collaborators from the 90s and early 2000s. It's actually a bit more than catastrophe theory. So catastrophe theory embeds naturally in so-called singularity theory. And what these chemists achieved was using electron density, or that goes back actually to Bader, and Sylvie used the localization function eta, to describe certain topological aspects of chemical processes, in particular reactions. Now,
Use that right here.
which one? Okay, so the function, the rho is the electron density, and eta is the so-called electron localization function. Those are both real valued smooth functions on R3, and they have critical points, and they have indices 0, 1, 2, and 3. So I use language here from catastrophe theory or in general singularity theory. So the index of a critical point is the number of negative eigenvalues of its hashing. Just a side remark, in case you read Sylvie's article, he has slightly different notation. So he has the index as the positive number of positive eigenvalues. But I've chosen to use the standard mathematical number as an index, which is then also coherent with how Connor described catastrophes in terms of potential functions. So we get a dynamical system, and that's r dot is, or the time derivative of r, and here r is a curve in R3. It's given by minus the gradient of v of rc. So r, those are the so-called internal parameters, and c are the external parameters, and the v is in this case negative rho or negative eta, depending on what you choose. Actually, as has been shown in modern chemical language, and probably even better function would be the minus the Laplacian of the electron density, but that is something which probably needs to be further investigated by mathematical physics and chemistry means. Okay, and now these critical points and how they are connected determine a molecular graph in the language of Bader, and provide information about possible reaction processes. So this is exactly in the major goal of the Delta project, and so we definitely should look at what chemists have done in that regard already. So let me now come to a particular example, namely the ammonia molecule. And it's a well-known effect that the ammonia molecule has an inversion, and that can be described kind of like flipping an umbrella. So if you look here at the ammonia molecule, in the center you have nitrogen, and then at the bottom you have 3 hydrogen atoms, and on top you have the 2 non-binding Lewis electrons. And what can happen is, by quantum mechanical reasons, is that these 3 hydrogen atoms sitting below the plane where the nitrogen atom sits, they can go through that plane and flip over to the top, and the Lewis electrons go down. And that is a process which was, by the way, found in the 1930s, I think 1935, by chemists, and which needs obviously a theoretical explanation. And with the language of chemistry, you can achieve that. Let me just introduce some more notation. So the vertical axis is the z-axis, and it's in the language of symmetries of molecules, it's the C3 axis, or in more mathematical terms. So the group Z3 acts by rotation, and it just rotates the 3 hydrogen atoms. Okay, the horizontal plane is the XY plane, and the N is the center of your coordinate system. And this inversion of the ammonia molecule is actually nothing else than mirroring the whole molecule at this XY plane. Just some chemical data. The angle phi between the XY plane and the NH bonds is negative 21.6 degrees. That can be measured. Okay, here is the citation for the experimental detection of ammonia inversion from 1934 by Clayton and Williams. So now let's come to the critical points of this kind of potential function. V is negative eta, or V is negative rho, and it's a slight modification of a table in the work by Sylvie. So the local minima are those where the index is 0, and these are the so-called attractors. So where the electrons, or better electron pairs, kind of want to go to. Again, the index was the number of negative eigenvalues of the Hessian. The rank is just 3 in all these cases. The rank is 3 when the critical point is non-degenerate. So here we do not yet have a catastrophe because the rank is maximal, so the Hessian is invertible. And the signature is the difference between the number of positive and negative eigenvalues. Local maxima are just the opposite. They are repellers, and the index is 3. And then there are 2 types of saddle points of index 1 and of index 2. And out of the rank, then you can immediately compute what the signature is. Okay. So this reaction coordinate theta, this is pi half plus phi. So if I come back here, so the angle phi was the angle between the xy plane and the NH bonds. Well, I switched between radian and degrees, but that's I think okay. And then what one can show by considering the numerically achieved data for ammonium inversion is that this eta has, after appropriate coordinate change, the following form as written down here in this formula. It's eta is x cubed minus 3x squared plus wx squared plus y squared plus ux plus vy. Let me just explain all those variables. So x, y are the coordinates in the plane, and we do not have the z value here. It's replaced by the control parameter w, which is plus or minus negative phi c minus phi. So phi was this angle I described before, and phi z is the value of that phi where there is a bifurcation, meaning that's exactly where the catastrophe happens. And it can be measured that this, or actually theoretically determined even, that it lies at plus or minus 15.2 degrees. So the coordinate z is regarded here in this as an external parameter, but this is totally fine. And u and v are just these parameters, as Connor has explained. For this universal unfolding, you need a certain number of external parameters, and this uv kind of can be interpreted from a chemical point of view as breaking off the Z3 symmetry. Definitely there's a lot of theory involved, and but nevertheless, we have a catastrophe here, and it happens exactly, so you go from where the hydrogens are at the bottom, so at a stable level, and then you can move those up until you are at a planar level. I will in a second show a picture, and then you can move further up until you have the 3 hydrogen atoms above the nitrogen. So when the flipping of the umbrella is completely achieved. And while doing this, the whole system goes through 2 catastrophes. And these are described exactly by this unfolding, which according to the language of René Thom are elliptic umbilics. Okay, let me just, at the end of this webinar, give you the molecular graph of NH3 in this catastrophe theory language, so to speak. So here we have N3 in the center, C of N. That is where the nitrogen atom lies. At the bottom, we have the 3 hydrogen atoms, and at top, we have the 2 Lewis atoms. And altogether, these gives 1, 2, 3, 4, 5 critical points of index 0. Now, if you go look at where the situation where the NH3 molecule, the ammonia molecule, is planar, you can compute the corresponding electron localization function, and then you get one more critical point of index 0, and that can be achieved computationally. Yeah, this has been done. Again, I cite here the work by Sylvie, and there's obviously some more explanation than I can give in the short time of a webinar. But in any case, it shows that the catastrophe theory and its topological implications give highly important and valuable information about the chemistry of the molecule one considers. And the suggestion would be to continue with this and study other molecules besides ammonia. Actually, this obviously has been done already to a certain degree, but looking at the Delta project, it probably would be a great idea to look at the electrophilic attack molecule or the alkanes and see in how far catastrophe theory can help describe the reaction in the electrophilic attack model or certain features the alkanes have. So let me conclude finally with citing the references. I also would like to mention Samsung, who in addition to Connor and me contributed to this project. So Sam wrote the
three-dimensional demo.
He wrote the three-dimensional demo, exactly. And then here are the various works by Bader. That's the first one. Castrigliano, that's a highly readable book by on catastrophe theory. Clayton and Williams, that was the experimental detection of the ammonia inversion. The fourth one is the work by Sylvie and collaborators on the catastrophe theory interpretation of ammonia inversion. And the last one, that's a certain other reference where catastrophes are visualized, have been visualized. Thank you for your attention. Are there any questions?
Well, prior to questions, thanks very much to Connor and Markus and also to Sam for the fantastic talk. So let's go ahead and unmute ourselves and give them a round of applause. And then as Markus asked, further questions?
Let me ask a question about, so if you have just a sample of points from a space or a surface, to build a catastrophe surface of that sample, do you have to first get the kind of closed form using these algebraic geometry methods and then go about it, or is there a direct way to get approximation to the catastrophe surface?
So to my understanding, the software of doing catastrophe theory is not as elaborate as, let's say, topological data analysis or other software packages. So our hope and expectation is that via use of algebraic geometric methods, one could get a hold of this. And Connor has pointed out on a contribution to Slack and on the GitLab that the recent work by Sturmfels and others on how to use or detect varieties via algebraic geometric methods from samples, that could be a viable approach to do exactly what you suggest. We are not there yet, but I think it would be a great approach. And the other point is, and again, I refer to what Connor has said during the talk, the main thing you have to consider are actually the ring or algebra formal power series. And from a mathematical point of view, there's something really nice about those. Those are Noetherian rings. So they are finitely generated and all their ideals are finitely generated. So you can use algebraic geometric methods which are computable. Yeah, so you can really throw a computer at those problems, but the approach is different to, let's say, meshing, and so the standard approach you use usually when you do geometry and topology, but it is topological of its nature.
Mm-hmm. So in fact, as an extension, would it make sense to study the topology of the catastrophe surface? Or is that information already there in everything that you explained or you extracted while building the catastrophe surface?
It's not, it's a bit more than the catastrophe. It would be the whole picture, but definitely let's see the kind of graph or how you divide whole space by the singularity points and the singular points and the the connectivity, meaning if you have such a dynamical system, if you draw the geodesic, so to speak, when falling in such an attractor. So if you take the whole package, yes. Yeah.
Okay.
So it's not just, yeah.
And in particular, the bifurcation set would probably give you more interesting information than the catastrophe surface as a whole, because that's sort of the subset where you have this interesting behavior. The entire catastrophe surface is just going to, a lot of those are going to be non-degenerate critical points.
Okay, thanks.
Other questions? I'd maybe a question or two. So the first part would be when you're saying sort of using algebraic geometry, for example, Sturmfeld's works on variety identification for use in catastrophe theory, you sort of mean you sample points in space along with the function values, and then pretend you knew the diffeomorphism. Pretend you knew the diffeomorphism under which locally this looked like one of those algebraic functions, and then try to recover that algebraic function. Is that loosely what you mean?
So for the algebraic geometry methods, you've got your points and you try and find polynomials on which they all vanish or nearly vanish.
That's right.
And then based on those polynomials, you can, the variety is just the set of all points where all the polynomials vanish. And so.
And your application to catastrophe theory is to find the, the different singularity types locally, which are all expressed as these polynomials. Is that right?
Right. Well, I mean, once you had the variety that the points are sampled from, then you could use that to figure out what sort of the type of
I see. You're saying
critical point it is.
It's not really say it's sort of like pretend you have points sampled from a variety, and then you want to identify the catastrophe locations or the critical points and what types they are.
Yeah, exactly.
I see.
So related to that and kind of expanding and thinking about energy landscapes, let's say we had a series of energy landscapes that were all representing slightly modified chemical systems that maybe have different, maybe slightly different barriers or whatever have you. I think in the original discussion associated with catastrophe theory, we kind of put out there that if we have this series, we could use catastrophe theory to understand at what point along this kind of set of surfaces, there would be, if you will, an irreversible change or your catastrophe is occurring. And so the way, I guess I'm trying to cast this because initially when you were talking today, you were talking about like a single surface that you were kind of modulating, right? Like in your example, you were modulating the mass, right? But here we've got like these there's no continuous, how do I want to say this? There's no continuous function that maps one surface onto another surface if we change and have a series of like 5 or 6 energy landscapes, right?
Okay.
And so I'm curious because it would seem to me we would need to do something to be able to map the points from one surface to another surface, if you will, in order to be able to identify catastrophes along that series. Does that make sense?
Yeah, I kind of see what you're saying. I'm not exactly sure how to approach that problem off the top of my head. I mean, Markus, do you have any thoughts?
Yeah, I mean, in general, I think, again, I'm referring to what Connor explained. By introducing additional parameters, you make something non-singular out of something singular, so to speak. And that approach could help here. There's definitely, it's not a complete answer, but it is an approach which works mathematically, and I think this is a route one should go. and then finding the universal unfoldings, that's again finding, so to speak, the minimal one of additional stuff you need. The big difficulty is that the higher you go, and the higher with those co-ranks you go, the more uncertain is the mathematics. Yeah, so in this initial stuff of the 7 elementary catastrophes, things are settled. So actually with the work of René Thom and then later on Vladimir Arnold. But if you go higher, then it can be pretty wild and a lot is not known. Yeah. Nevertheless, it is an extremely powerful method, and the question arises, if you have an energy landscape, do you only have Morse critical points, or do you have catastrophes in there? Meaning, do you have critical points which are degenerate? And if they are, you need to describe them. And that is something where my expectation is it's hard to find with meshing, but more with algebraic geometric methods. But this is a principle, I think this would a principally new idea, new aspect of this energy landscapes, and to my knowledge, it's not solved. I mean, it's not.
Yeah, I mean, truly degenerate critical points are really rare in chemistry, at least for complex systems. It's certainly true in something like rotational barriers of, simple molecules or something like this. You have truly degenerate energy minima or degenerate maxima. But generally it requires a huge amount of symmetry and something that's isolated and not like an isolated molecule and not anything where there's intermolecular interactions or something like that. So when you get to more complex chemistry, the likelihood of that happening is a lot less. I do think it would be really interesting if we could devise a test system that was a chemistry system for which we had a variable that we were perturbing with a relatively simple energy landscape to be able to kind of show a more complicated or relevant kind of chemistry example, right? And so, it could be maybe, I don't know, maybe in these Leonard-Jones fluids, for example, if you have a bidisperse fluid and you have a relatively continuous change in the relative sizes of the Leonard-Jones particles, that gives you a series of energy landscapes where maybe we can create some kind of, you can use that variable to create a mapping of the underlying energy landscapes to one another. I'm not sure, but we should think about it, because I think it would be really, really cool to show an example of this for the Delta project. But we need to think about it carefully.
I just had one comment. I don't know if I'll make it to a question or not. So the Sternfels work, which I quite like, you're sampling from this algebraic variety and then trying to determine the variety. If there's noise, those particular techniques sometimes have problems. So it's not very robust to noise. And that makes me think about the diffeomorphism aspect. No chemical energy surface is going to live on an algebraic variety. It's just going to be locally diffeomorphic to one. So I'm curious, of other techniques for, like, for example, distinguishing those 7 classic catastrophes from each other. So how well does sublevel set persistence do? Or if you add on to sublevel set persistence and do some multidimensional things, how well can non-algebraic methods do it at distinguishing those, just as a potential parallel route of thought along with algebraic geometry stuff. Very interesting talk. Thank you so much. I learned a lot. Other questions? Thanks so much, everybody.
Thank you.